Hello and welcome to today's lecture. Continuation from where we start on power cycles, and today we'll be looking at steam power cycles. So starting from steam. Steam is the most common working fluid used in power cycles because of its many desirable characteristics, that is low cost, availability, and high enthalpy of vaporization. Okay, so that means in most power plants, steam is used in the process. Other working fluid used include sodium, potassium, mercury for high temperature application, and some organic fluid such as benzene and the freons for low temperature applications. Okay, and most of the appliances and equipment that we use, household equipment actually, they make use of some of this working fluid. Steam power plants are commonly referred to as coal power plants, nuclear plants, or natural gas plants, depending on the type of the fuel used to supply heat to the steam. But the steam goes through the same basic cycle in all of them. So therefore, all can be analyzed in the same manner. Okay, so this just means that the different types of fuel that could be used to get generate steam are just the coal, the nuclear, and the gas. That's what is in current application now. Okay, in more sustainable, or should I say sustainable application, is the burning of trash to generate steam as well to uh, for power generation. The steam goes through a cyclic process. The generation of steam in a boiler, as you can see in the diagram here, and the partial condensation expansion in the turbine. This is where the steam, the working fluid, does a work to move the shaft in the turbine to generate electricity. Then the condenser, so the turbine is the steam expands in the turbine and condenses here in the condenser. So with the picture shown in the second slide in this lecture, you will see the cooling tower. So that will represent the condenser. Okay, and the low quality steam and mixture of steam and liquid will go to the pump feed, and that will be pumped back into boiler by increasing the pressure. Okay, so these processes are accompanied by others depending on the cycle used and the complexity of the plant. So the steam power plants, the working fluid is steam and it is completely enclosed. In a coal or natural gas-fired power plant, the boiler tubes separate the combustion gases from the steam. So the thermal efficiency of the engine is equal to the ratio of the net work output, okay, the work leaving the system as the working fluid does the work, divided by the total heat supplied to the system, okay. You can write this equation taking into account only the heat in and heat out. Then the equation will be in the form of 1 minus the heat lost from the system divided by the total heat added to the system. And the formula for the network is the total heat added to the system minus the heat loss. So recall from previous work, the work ratio is given as the network divided by work the work out of the system. Okay, so and this is used to compare the actual cycles and evaluate the cycle sensitivity to irreversibilities. So if the work ratio is only slightly greater than zero, a small amount of the process reversibility will significantly reduce the cycle efficiency. And if the work ratio approaches unity, a small amount of the process reversibility will lead to a small reduction in cycle efficiency. Okay, so a combination of a high ideal cycle efficiency and a high work ratio provides a reliable indication that a ray power plant will have a good overall efficiency. So the work ratio also serves as a useful criterion for comparing the relative size of the plant for a given power output. So the component producing the work output has to provide the power for the component requiring the work input. The work ratio approaching unity therefore indicates that these components will be at least possible size for a given net power output. So the work ratio of most practical vapor cycle are very near unity, and the work ratio is not very informative. A more direct criterion for size is required. So therefore, the volume of the working fluid passing through the cycle components could be an indication of their relative sizes. A more direct measure of this is the steam power plant is a specific steam consumption, which is SSC. So the specific steam consumption is defined as the mass flow of the steam required for per unit power output. So this is given as a kilogram per kilowatt hour. Okay, and it's equal to 3,600 divided by the net power. Okay, remember this is an absolute net power, so we should be looking at a positive number here. So we have mentioned repeatedly that the Carnot cycle is the most efficient cycle operating between two specified temperature limits. It is then natural to look at a Carnot cycle first as a prospective ideal cycle for vapor power plants. So consider a steady flow Carnot cycle executed within the saturation dome of a pure substance. Okay, here represented on a T temperature entropy diagram. So, what is a Carnot cycle? So, the Carnot cycle is one where steam is generated in the boiler, and this steam goes into the turbine where it expands, and that expansion of the steam helps move the shaft in the turbine, and as it moves the shaft in the turbine, it loses quality. Okay, and the steam leaving the turbine passes to the condenser where some of the vapor is condensed, then pumped adiabatically. Okay, remember in the turbine there is adiabatic. Uh, the turbine is adiabatic, so there is no heat added. But in the boiler, there is heat added. Okay, and this condenser is pumped adiabatically uh, back to the boiler. Okay, so the adiabatic operation happens at the compressor and the expander. Okay, so what happens at point 1 to 2? So the process 1 to 2, this is where the fluid enters the boiler at point 1. So the liquid that enters there is a saturated liquid, and the fluid is then heated reversibly and isothermally, okay, at constant temperature, and the boiler is basically a large heat exchanger where the heat originating from the combustion gases slash the nuclear reactor is transferred to the water at approximately constant pressure. The fluid leaves the boiler as a saturated vapor. Okay, saturated vapor goes to this point. Remember, this is the critical temperature, and the distance between here to here is just converting from liquid to vapor, saturated vapor. So at process 2 to 3, okay, at stage 2, uh, the saturated vapor enters the turbine, and in the turbine is expanded isentropically. So this simply means that the entropy remains the same as the steam is expanded in the turbine, and the turbine as well is adiabatic, meaning there is no heat added in that process. Okay, and this produces work by rotating a shaft connected to the electric generator. So the pressure and the temperature of the steam drop during this process to a value at state 3. Okay, so the temperature drops and the pressure drops as well, but the entropy remains significantly the same. Okay, because it's an isentropic process here. So as you can see on the x-axis, that the entropy will be the same at this point between 2 and 3, and also at the point between 1 and 4. Okay, but there is a difference in temperature. The temperature of the steam here, if you measure it against the y-axis, you see that there is a difference in temperature at point 2 and point 3. Similarly for point 1 and point 4. Okay, the fluid is determined as a saturated liquid from the stage 2. Okay, at, at stage 3, yeah, the fluid leaves the uh, at saturated liquid and vapor mixture up to stage 3. So at the stage 3, the saturated liquid and vapor mixture enters a condenser here, okay, and this is reversibly cooled and atomically cooled in the condenser, And the uh, condenser is basically a large heat exchanger where heat is rejected to a cool medium such as lake, a river, or atmosphere, or at a approximately constant pressure. So the fluid leaves the condenser here as a saturated liquid vapor mixture, and that saturated liquid vapor mixture goes into this pump, kind of like a pump, okay, or compressor in this case. So the compressor, so the saturated liquid vapor enters the stage 4, which is a pump, and the pump will compress asymptotically, as we mentioned already, at constant entropy. Pumps the liquid, now the saturated liquid vapor mixture, up to the pressure and the temperature, okay, compresses it to a saturation pressure required at the entry of the boiler. Okay, so the operating pressure of the boiler, we use the pump to get the liquid saturated liquid vapor mixture up to that pressure required for it to enter the boiler. And this temperature reading here will give the corresponding saturation temperature against the target pressure of the boiler. Okay, so the pressure and the temperature of the fluid increase during the process to the value at state 1. So the fluid leaves the pump as a saturated liquid at the initial state. Okay, so like we said already, the heated reversibly anisothermal in boiler, and the liquid leaves here as goes from a saturated liquid to a saturated vapor here, and that the saturated vapor does the useful work in the turbine as it is expanded isentropically, okay, and the mixture of the low quality steam now, which is a saturated liquid vapor mixture, goes into the condenser where most of the heat is removed from this working fluid, and then the fluid goes into the compressor, stay while remaining as a saturated liquid vapor mixture. And in this compressor, uh, most the mixture of liquid and vapor is compressed to raise the pressure to the boiler pressure, so that it will not be transported back to the boiler and the process continues. So to replicate what happens at the different regions using a TS diagram, and you can see that the heat is added in the boiler, so there was a net heat change or latent heat required to boil the compressed liquid or saturated liquid to change phase from point 1, which is a liquid phase, to a vapor phase at point 2. Now, there will be work done at point 2 here, and that work done by the fluid is the useful work done in the turbine, and the low quality steam goes to point 3 where it is cooled further to reject most of the heat, and it goes to the pump, and the pump compresses the working fluid back to the so that it's a work. So the work done by the pump, which is a positive work done by the pump, uh, to get the pump to the boiling pressure at the boiler, to pump it back to the boiler, is given here on this region. Okay, this is very important because when we do the calculations, you will understand what we mean by this definition of the different stages within the cycle. So the thermal efficiency of an engine is equal to the ratio of the network output to the total heat input. So as we've already defined this. So if you recall, for the reversible Carnot cycle, the thermal efficiency can also be expressed as the 1 minus the temperature at the lower reservoir divided by the temperature at the higher reservoir. So the bigger the difference between the two temperatures, the higher is the efficiency of the cycle. So the efficiency of all heat engines, whether reversible, ideal, or actual, are increased when the average temperature at which the heat is added or absorbed is increased, and the average temperature at which the heat is removed or rejected is decreased. However, efficiencies are lowered by reversibilities. So the lowest possible temperature of the condensing steam, which is the temperature at a lower reservoir, is governed by two factors: the temperature of the sink of heat of the sink of heat, such as atmosphere, ocean, or river. So normally the ocean is measured as an average temperature of 15 degrees Celsius. Okay, this temperature may be lowered by using a refrigeration cycle, but this is not cost effective. Okay, imagine trying to cool down the temperature of a lake using a refrigeration cycle. So it's very, very expensive to do that. Okay, so the efficiency depends on the capability of this low temperature reservoir to remove heat, the amount of heat, the total amount of heat they could remove from the system, then that will help aid with the efficiency of the system. Okay, the lowest possible temperature of the condensing steam, TL, is governed by the two factors. And the second factor here is that the temperature difference between required for the heat transfer process, which is the rate at which heat transfer is proportional to the surface area across which heat flows, and the temperature difference between the condensing steam and the cooling fluid. Then in practice, the required rate of heat transfer can be obtained with a reasonable size of condenser if a temperature difference of 10 degrees Celsius or 15 degrees Celsius is provided. So the lowest practical condensing temperature in a cycle is therefore 25 degrees Celsius to 30 degrees Celsius, with the corresponding saturation temperature being 0.032 bar and 0.042 bar. So the figure below shows the variation of cycle efficiency with condenser pressure calculated for a constant boiler pressure at 30 bar. Okay, and on the y-axis we see the cycle efficiency, and on the x-axis we see the condenser pressure. And as you can see, as the pressure drops, okay, then the cycle efficiency increases. Okay, so meaning that the lower the temperature, the higher the cycle efficiency. So the maximum possible temperature of the working fluid TH is also governed by two factors. The first one being the maximum temperature and the strength of the material available for the highly stressed parts of the plant, so the boiler tubes or the turbine blades. So this metallurgical limit may be assumed to be 600 degrees to 650 degrees for steam plants, but the exact figure depends on the required plant lifespan. So the critical temperature of the working fluid, as a Carnot cycle operates with steam in the wet region, that is a mixture of vapor and liquid, that's low quality steam. The highest possible temperature is that corresponding to the critical temperature for water, which is 374.15 degrees Celsius. We have established this uh, in the second lecture, I guess, or the first lecture, where we plotted the TS diagram using the critical temperature. And here is the critical temperature of steam or water in this case, and also the corresponding critical pressure of water at that temperature. So this imposes limitations, and it is not possible to take advantage of the abilities of modern materials which cannot be used to their best advantage when steam is being used as the working fluid. So the effect of the boiler pressure on the cycle efficiency and steam consumption for a constant condenser pressure of 0.04 bar is shown below. And as you can see, the cycle efficiency increases as the boiler temperature, okay, increases. But the limit, as we know, is the critical temperature. Okay. So as we increase the boiler pressure, there is only a small gain in cycle efficiency. The cost of the boiler, pipe works, as well as the turbine casing increase. The specific steam consumption and hence the size of the plant increases after a certain pressure is reached. An economic analysis of combination of capital costs and operating costs for different pressures is used to determine the optimum operating pressure. So the first example here. So a Carnot cycle operates between 30 bar and 0.04 bar. So calculate the heat transferred in and out of the system per unit mass, the work transferred in and out of the system per unit mass, the cycle efficiency, the specific steam consumption, and the work ratio. Now we already know for heat transfer occurs in the boiler. So what did we do with the heat? We boiled water to convert to steam, saturated steam. So here should be the heat added to the system. Now there is a kind of work done by the steam at the turbine here. So the steam doing work is a negative work output here, okay, because the steam does the work. Now there is a condensation work that goes here, and that condensation session here we allow is for heat loss. Okay, we need to extract all the heat within the working fluid to so there will be heat loss between 4 to 3, between 3 to 4. Yeah. So it from another work will be done, but here is a positive work done by the system to the working fluid, and that work is done by a pump or a compressor. That work is done by a compressor to get the fluid coming in here from point 3 to the boiler pressure and temperature to get it to the operating pressure and temperature, saturation temperature for entering the boiler. Okay, so how do we tackle this? With this information that we've already established, so we can go straight ahead to define what happened here. So the latent heat, okay, required to convert water to steam here, which could be written uh, as the total heat in is equivalent to the change in enthalpy. And this is based on the first law, okay? Now remember, we are disregarding the effect of kinetic energy and potential energy because in most cases within the boiler, the change in height from the inlet and the outlet is very negligible. Similarly to uh, the change in height in the turbine. So potential energy are usually disregarded. Now, because it's a closed system, okay, the kinetic energy, the kinetic energy, mainly the one of the variables here of concern will be the velocity of the fluid passing through the cycle will remain damn near constant. So the changes in the velocity will be very, very little, okay? And because of that, we can disregard the kinetic energy. But on the other hand, the enthalpy, the change in enthalpy is the only thing remaining in our first law, energy balance, okay? And we can use that to calculate most of the sections within this, okay? So if we define what the total heat addition actually means. So that means the heat added to point 1, which is the boiler, to get the liquid to convert to vapor, and that is given as the change in point 1 and 2. Okay, total heat added here and the final, so the enthalpy here minus the enthalpy here. Okay, so the work done by the steam at this point, okay, so that we can calculate that, which is W2 to 3 at point stage is 2 to 3, and that has to be a negative, okay, work output because the steam itself, the working fluid did the work. So it becomes a negative change in enthalpy of these two positions, okay. The heat lost as the working fluid is condensed further is condensed. The heat lost by the system is given as the Q, the enthalpy change in enthalpy from point 3 to point 4. and the work done by the pump at point 4 is given as the change in enthalpy, okay, as the change in enthalpy from point 4 to 1, okay. So applying this information, so we go to the steam table because the question says that the pressure is at 30 bar. So we go to the steam table. So at point 1, we know that it's liquid in the boiler. So we look for the corresponding values for the enthalpy and the entropy as well. So for a steam table 30 bar, so we go under pressure. So under pressure 30 bar. So we find 30 bar. So we find the corresponding enthalpy of HF. Okay. So the best is to use further properties of water and steam. So pressure at 30 bar. So you can do an interpolation to find where is it? Okay, not this one. Give me a minute. So we have entropy and enthalpy. Okay, so all of it is here. So saturated water and steam. So you go for pressure at 30 bar. Where is it? So 30 bar, I hope you can see this clearly. So we are looking for HF for 30 bar. So the HF for 30 bar is this, okay, 1008 kilojoule per kilogram Kelvin, and the SF is what? 30 bar, 2.645, okay. So we get those values here, okay. Then what do? We do the same at point 2, okay. At point 2, we do the same. We go to 30 bar because they are at constant pressure, okay. You see the line? It means that this point and that point are the same pressure. So it's an isobaric, an isothermal uh, combustion in the boiler, okay, heat addition in this case. So we get the corresponding enthalpies, which is the H2, enthalpy at point 2, and entropy at point 2. So at point 3, what do we do at point 3? So the pressure, as the steam expands within the turbine, it loses pressure, and if for the pressure falls to 0.04 bar. So we go to steam table, but we know that the steam here is a low quality steam, so it's a mixture of a saturated liquid and saturated vapor. So if we go to the point, the pressure is, since the pressure at this point is 0.04 bar, then we need to find the values for the enthalpies and the entropies for both the gas and the liquid. Okay, we do that for saturated liquid vapor section. Okay, if we go here, we go to where is 0.04. So we have 0.04 bar, okay, which is at this point. So we find the corresponding HF, HG, right, SF, and SG. Okay, when we find that, then we need to calculate for the actual enthalpy H3. Okay, how do we find that? Because this enthalpy here is a combination of the enthalpy of the vapor phase and the enthalpy of the liquid phase. Now we need to identify what is the actual quality, so the dryness fraction of that steam. Okay, it's a low quality steam from this, but what is that quality? So we can use the formula for finding the dryness fraction or the quality, making SF subject of formula. If we know SF, okay, if we know the uh, the entropy, okay, at this point, oh, wait a minute, at point S3, okay, since this process here, the expansion process at the turbine is isentropic, and this means that stage 2 and stage 3 we have the same entropy. Okay, so since we know the entropy at S2, that means the entropy at S3 will be the same. And if we since we have established this now, we can use the value provided for S2, the entropy at S2, to sub for S3 in this equation to find the quality of the steam at this point. And once we know the quality of the steam at this point, then we can use the similar equation but rewrite it with respect for the enthalpy. Okay, remember few notes ago, I think last lecture as well, uh, uh, I showed you how to derive the equation for the dryness fraction or the quality, and how to use properties like internal energy, entropy, and enthalpy to find the value of the dryness fraction if any of these physical properties are known. Okay, so we can use the same. Since we know the entropy, then we can calculate the dryness fraction. And if we know the dryness fraction, we can do similar equation. This equation and this equation is the same. The only difference is that this is dealing with entropy and this is dealing with enthalpy. So if you can replace enthalpy with any place you see entropy, then you make H3, in this case, subject of formula, and you can add the value that you got from for the quality, then you would arrive at the enthalpy at H3, okay, the enthalpy at point 3 or stage 3. So we do the similar thing for stage 4. So, but we know that what we have here at the stage 4 is a combination of saturated liquid, okay, saturated liquid and saturated vapor. So we get we go at 0.04 bar, we find the values of the enthalpy and entropy for both liquid and gas at this pressure. Then we calculate for the quality. Since we know the entropy at point 1 or stage 1, and we know that this stage will happen isentropic, so meaning that they have equal entropy. If you look here on the x-axis, you will see that they have the same entropy. So meaning that if you know the entropy at this point, then you can use the dryness fraction expression with respect to entropy to calculate the dryness fraction or the quality. Now, if you know the quality of the steam here, then you can apply the same formula for enthalpy, but instead making H4 subject of formula to find the enthalpy at this stage. Okay, and once we have gathered all the enthalpies, then we can list all of them down. So it says for us to calculate the A part, which says the heat transferred in and out of the system. So we know where heat is transferred into the system, which is between point 1 and point 2, and heat is lost in the system at point 3 and 4. So what do we do? So the heat supplied to the system or the heat transferred to the system is now equal to the change in enthalpy at point 2 and point 1, which is the simple subtraction of the enthalpy at point 1 from the enthalpy at point 2, and gives us this value. Now, if we do the same for the heat lost by the system from the condenser to the boiler or the compressor, now from the condenser to the pump or the compressor, okay? So that will be the change in enthalpy between these two stages, okay? It is now change in enthalpy of 0.4 minus enthalpy at 0.3, and we arrive at this. So this is the heat lost from the system, okay? So the B question asks us to calculate the work transferred in and out of the system as per unit mass. So the work transferred in and out of the system is between these 2 points. So the work done by the steam in the turbine uh, is between these 2 points, and the work done to compress the low quality steam and bring it up to pressure, up to operating pressure of the boiler, is between these 2 stages. Okay, so if we do a change difference in enthalpy between point 2 and 3, stage 2 and 3, and that will give us the work done by the steam, which is the work lost. And the positive work done to the fluid or the steam, the working fluid is done at this stage. Okay, so we take the difference of that. So it becomes H4 minus H3, H4 minus H1, and it gives us the work done by the pump. Okay, So it says calculate the cycle efficiency. We know that the efficiency formula for efficiency is the net work divided by the heat total heat added to the system. So we know the total heat added to the system, which is this, and we know the net work done by the system. So the net work done by the system is what is given as the work done by the steam plus the work done by the pump. Okay, so and that gives us this. So when this is added and we divide it by the total heat added to the system, and that gives us a 40% efficiency of the cycle. Okay, so the consumption of steam could be calculated. The SSC, we know the formula as 3600 divided by the network. Okay, remember the absolute means that there is no negative sign. Okay, this should have been the network done by should be negative, but obviously the absolute sign removes the negative, and the value of the steam consumption is almost 5 kilogram, damn near 5 kilogram per kilowatt hour. Okay, so every kilowatt hour consumes up to 5 kilogram of steam. So the work ratio, the formula for the work ratio is the net work uh, divided by the work done by the steam. Okay, so then that gives us 0.77. So in practicalities associated with this cycle. So number one, the isentropic compression stage, okay, between 4 and 1 involves the compression of liquid vapor mixture to a saturated liquid. So there are two difficulties associated with this process. Number one, it is not easy to control the condensation process so precisely as to end up with the desired quality at stage 4. Okay, so if the quality of steam coming to the stage 4 to the pump is not the amount of heat expected to remove is not removed properly, then there is problems. Okay, meaning that the compression might not work properly to give you the required operating pressure at this point. Okay, so it is not practical to design a compressor that can take a mixture of liquid vapor and discharge a saturated liquid. So pumps work with liquids, compressors work with gases. Okay. So impracticalities associated with the cycle at stages 2 to 3. So this is where I think I've mentioned some of this already, but the asymptotic expansion process between 2 to 3 can be approximated closely by a well-designed turbine. However, the quality of the steam decreases during this process. So the turbine has to handle steam with a high moisture content. Now, the liquid droplets impinging on the turbine blade causes erosion and is a major source of wear. Steam with qualities less than 90% cannot be tolerated in the turbine. Okay, so the isothermal heat transfer to and from the two phases, the two-phase system is not difficult to achieve as maintaining constant pressure will automatically fix the temperature at a saturation value. So the process 1 to 2 and process 3 to 4 can be approached closely in a real boiler/condenser. Okay, limiting the heat transfer process to two-phase system, however, limits the maximum temperature that can be used in the cycle. This limits the thermal efficiency, and any attempt to raise the max temperature in the cycle will require heat transfer to a single phase fluid, which isn't easy to accomplish isothermally. Okay, so fixing the temperature and trying to do this cannot be achieved. There has to be changes, and these impracticalities affects the Carnot cycle. Okay, so the Carnot vapor cycle is not used in practice due to the practical difficulties associated with the compression of the mixture of liquid and vapor. It is not practical to design a compressor that handles two phases. The difficulty to control the condensation process so that it stopped at stage 4. Okay, its low work ratio, and because of this, it is not used in practice. Okay, so it's just a process to which is a cycle to which we can base our modeling and our real life application, but replicating this is impractical. Okay, for next lecture I'll be going into ranking cycles. Okay, and you will get to see a bit of difference between the ranking cycle and the Carnot cycle as well. Okay, so see you on the next lecture.